Most drivers enter a road tunnel, follow the lights for a few minutes, and emerge on the other side without giving the structure around them much thought. But behind those walls can be one of the most complex transportation systems ever built. Some tunnels cut directly through mountains, others pass beneath rivers, cities, or even the seabed. Some are excavated by explosives, others by machines weighing thousands of tons, and some are assembled in giant sections before being lowered underwater, and the tunnel itself is only part of the engineering. Behind the visible roadway are ventilation ducts, drainage systems, fire protection, emergency passages, cameras, sensors, electrical networks, and control rooms constantly monitoring what happens inside. So today we're breaking down the major types of road tunnels, how they're built, why engineers choose one design over another, and what makes them safe enough for thousands of vehicles to use every day. Let's start with one of the most recognizable types. The mountain tunnel. Mountain tunnels are built through hills and mountain ranges, allowing roads to pass directly through terrain that would otherwise force vehicles to climb over it or travel around it. Without a tunnel, mountain roads often require steep gradients, sharp switchbacks, and much longer routes. By cutting through the mountain instead, engineers can reduce travel distance, lower road gradients, and create a more reliable connection between two regions. But a mountain that looks completely solid from the outside can hide complicated geology inside. Engineers may encounter fractured rock, underground water, unstable zones, or dramatic changes in rock strength. Depending on those conditions, excavation may be performed using drilling and blasting, mechanical excavation, or a tunnel boring machine. As the tunnel becomes longer and deeper, the engineering challenge grows. Ventilation becomes more important, water has to be continuously drained, emergency access becomes more complicated, and the enormous pressure of the surrounding rock has to be controlled by reinforcement, concrete linings, rock bolts, steel supports, or combinations of these systems. What appears to be a simple opening through a mountain can actually be an underground highway surrounded by an enormous support system, cut and cover tunnels. Not every tunnel is bored deep underground. When engineers need a relatively shallow tunnel, especially in an urban area, they may use a method called cut and cover. The concept is straightforward. First, engineers excavate a large trench from the surface. The tunnel structure is then built inside it, usually using reinforced concrete. Once the structure is complete, the excavation is filled back in, and the surface above it can be restored. Roads, parks, sidewalks, and sometimes even buildings can eventually occupy the space above the finished tunnel. The major advantage is accessibility. Because construction begins from the surface, building the tunnel can be simpler than excavating far underground. But there is an obvious disadvantage. During construction, the surface can be heavily disrupted. Traffic may have to be redirected, utility lines moved, streets closed, and nearby buildings carefully protected. So while the finished tunnel can become almost invisible, building it may temporarily transform an entire section of a city. Deep bore tunnels. When opening the surface isn't practical, engineers can go much deeper. Deep bore tunnels are excavated far below streets, buildings, railways, and underground utilities. Instead of digging a massive trench, engineers create access shafts and excavate horizontally beneath the city. One of the most impressive tools used for this is the tunnel boring machine, or TBM. A TBM is less like a giant drill and more like a moving underground factory. At the front, a rotating cutter head breaks apart rock or soil. The excavated material is carried away through conveyor systems or rail equipment. Meanwhile, directly behind the cutting head, precast concrete segments can be installed to create the tunnel lining. The machine moves forward and the finished tunnel gradually appears behind it. Different TBMs are designed for different ground conditions. Some are optimized for extremely hard rock. Others are designed for soft, unstable soil. Special pressurized machines can even excavate through water-saturated ground while preventing soil or groundwater from rushing into the tunnel. The major advantage is what happens at the surface, or more accurately, what doesn't happen. A city can continue functioning while an enormous tunnel is slowly being created tens of meters below it. Underwater tunnels. Sometimes the obstacle isn't a mountain or a city, it's water. Underwater road tunnels allow highways to cross beneath rivers, bays, lakes, and coastal waterways without requiring a bridge above the surface. But there isn't just one way to build them. One solution is the immersed tube tunnel. Large tunnel sections are constructed in a dry dock or fabrication area. The ends are temporarily sealed, allowing each section to float. The enormous segment is then transported into position above a prepared trench on the bottom of the waterway. It is carefully lowered, connected to the previous section, sealed, and eventually covered with protective material. The process is repeated until the complete tunnel stretches from one side to the other. The result is remarkable. Ships may travel across the water while thousands of vehicles pass through a highway buried beneath the bottom. But engineers can also build underwater tunnels without placing the structure directly on the seabed. A deep bore tunnel can be excavated through the rock or soil beneath a river or ocean floor. This reduces disturbance at the surface, but introduces another challenge: water pressure. The excavation may be separated from an enormous volume of water by only a layer of rock and soil. Controlling pressure, groundwater, and geological stability becomes critical. That's why underwater tunneling is considered one of the most technically demanding forms of tunnel construction. Twin-bore tunnels. Tunnels can also be classified by how traffic is arranged inside them. One of the most common modern highway configurations is the twin-bore tunnel. Instead of placing opposing traffic inside one large tunnel, engineers construct two separate tubes running roughly parallel to each other. One carries traffic in one direction. The second carries traffic in the opposite direction. This improves traffic organization and, more importantly, can improve safety. If a serious incident occurs inside one tube, emergency cross passages may allow people to evacuate into the other. Separating opposing traffic also eliminates the risk of normal head-on conflicts inside the main roadway. For major highways carrying large volumes of traffic, twin-bore tunnels are often an extremely practical solution. Two tunnels, two directions, one coordinated transportation system, single-bore tunnels. A single-bore road tunnel places traffic within one main tunnel structure. It may carry vehicles in both directions, usually separated by lane markings, barriers, or another form of traffic control. For roads with lower traffic volumes, this can reduce construction requirements because engineers only need to excavate one major tunnel, but using one tube for opposing traffic creates different safety challenges. Ventilation has to account for vehicles moving in both directions. Emergency response becomes more difficult, and incidents can potentially affect the entire route. For that reason, high-capacity modern highways often favor separated tunnel tubes where conditions and budgets allow. Parallel tunnels and cross passages. Some tunnel systems become even more complex. Several tubes may run beside one another, serving different traffic directions, additional lanes, maintenance access, or emergency functions. Connecting these tubes are cross passages. Drivers may barely notice the emergency doors built into the tunnel walls, but behind some of them are protected corridors leading toward another tunnel. During a fire or major accident, these passages can provide an escape route away from smoke, heat, and damaged vehicles. So what looks like a single tunnel from the driver's seat may actually be part of a much larger underground network. Straight and curved tunnel geometry also matters. Whenever possible, engineers may use a relatively straight alignment because it simplifies navigation and can improve visibility. But real terrain rarely gives engineers a perfect path. A tunnel may have to curve to avoid weak geological zones, foundations, underground infrastructure, protected areas, or other obstacles. It may also need to connect with existing roads at very specific locations. Inside a curved tunnel, visibility becomes especially important. Drivers cannot see as far ahead, meaning stopped traffic or an accident may remain hidden around the bend. Lighting, speed limits, warning signs, lane markings, cameras, and incident detection systems all become essential parts of the design. Inclined and sloped tunnels. Not every tunnel stays at the same elevation. Some gradually climb or descend underground. These inclined tunnels allow roads to connect points at different heights while remaining inside a mountain or below the surface. But road gradient has to be carefully controlled. Heavy trucks lose speed while climbing steep slopes, creating differences between vehicle speeds. On long descents, braking distances and brake temperatures can become more important. The slope can even affect ventilation because heat, smoke, and hot gases naturally tend to rise. So something as simple as the vertical angle of a tunnel can influence traffic flow, fire behavior, and emergency planning. Ventilated road tunnels. Then there is one system that almost every long road tunnel needs. Ventilation. Inside an enclosed tunnel, vehicles generate heat, gases, and airborne particles. Without sufficient airflow, those pollutants can accumulate. Large tunnels therefore use mechanical ventilation systems designed to continuously control air movement. Some systems use large jet fans mounted above the roadway to create longitudinal airflow along the tunnel. Others use dedicated ducts to supply fresh air or extract contaminated air at different locations. But ventilation becomes even more important during a fire. Smoke can travel rapidly through an enclosed space, reducing visibility and making evacuation extremely dangerous. A tunnel's ventilation system may therefore be designed not only for normal traffic, but also to control the direction and movement of smoke during an emergency. The air inside a tunnel is being engineered just as carefully as the roadway itself. Fire-safe tunnels. Vehicle fires are among the most serious emergencies tunnel engineers prepare for. In an open environment, heat and smoke can disperse into the atmosphere. Inside a tunnel, they are trapped. Temperatures can rise rapidly, smoke can spread along the roadway, and visibility can disappear. Modern tunnels therefore rely on several layers of protection. Fire-resistant structural materials can protect the tunnel lining. Sensors can detect smoke or abnormal temperatures. Cameras allow operators to identify incidents. Emergency lighting can guide people toward exits. Fire hydrants or suppression systems may help control flames. And protected escape passages give people somewhere safer to go. The objective isn't to depend on one perfect safety system. It's to create multiple systems that continue protecting people even if one layer fails. Smart road tunnels. And finally, there are smart tunnels. Modern road tunnels are increasingly controlled by networks of sensors, cameras, computers, and automated systems. Cameras can monitor traffic continuously. Radar or video analytics can detect a stopped vehicle. Air quality sensors can measure pollution levels. Temperature and smoke sensors can identify possible fires. Variable signs can instantly warn drivers about congestion, lane closures, accidents, or changing speed limits. Ventilation can automatically increase when traffic grows heavier or when air quality deteriorates. In some tunnels, an incident can be detected and reported to operators within seconds. And as vehicles become more connected, the tunnel may eventually communicate directly with them. Instead of drivers discovering an accident after entering the tunnel, their vehicle could receive the warning before they even reach the entrance. What looks like nothing more than a road disappearing underground can actually be one of the most technologically advanced sections of an entire highway network. Conclusion. From mountain tunnels carved through solid rock to enormous passages running beneath rivers and cities, every road tunnel exists to solve the same basic problem. How do you move traffic through an obstacle instead of around it? Sometimes that obstacle is a mountain, sometimes it's a river, sometimes it's a crowded city with nowhere left to build on the surface, and sometimes it's the sea itself. Engineers can blast through rock, excavate from the surface, bore deep underground, or sink enormous prefabricated sections into place. But excavation is only the beginning. A functioning road tunnel also needs drainage, lighting, ventilation, structural reinforcement, fire protection, emergency exits, traffic management, communications, monitoring, and constant maintenance. So the next time you drive into a tunnel, don't think of it as simply a hole through the ground. Behind those walls is an entire engineered environment designed to keep traffic moving through a place where a road normally couldn't exist. And now you know how the major types of road tunnels actually work.